In the early 1980s, our picture of the cosmos felt both vast and lonely. We knew the universe was expanding, but the local neighborhood seemed relatively stable. Then came the data. Astronomers like Vera Rubin had already confirmed in the 1970s that galaxies were spinning too fast. Well, they should have flown apart. Something unseen, some dark matter, was holding them together. This discovery set the stage for a new level of cosmic mapping. By 1982, a team led by John Huchra, Margaret Geller, and others began the CFA Redshift Survey. They were painstakingly measuring the distances to thousands of galaxies. Their goal was to create a three-dimensional map of the universe. And as they mapped, a startling trajectory became clear. The data confirmed what had been suspected for decades. Our nearest major galactic neighbor, Andromeda, was not moving away from us. It was heading right for us. Its light was blue-shifted, meaning it was compressing as it approached, not stretching out as it receded. The numbers were immense. Andromeda was closing the 2.5 million light-year gap at a speed of about 110 kilometers per second. That's fast enough to cross the continental United States in under a minute. The collision was inevitable. The calculations refined over the following years placed the event about 4.5 billion years in the future. This wasn't just an abstract idea anymore. It was a forecast. Our home, the Milky Way, had a destiny, a violent, chaotic, and ultimately creative merger that would forge an entirely new galaxy. This concrete prediction, this future cataclysm written in the stars, made people think. If the universe had such a dramatic future, what about its past? The Big Bang Theory provided a powerful story of the origin. But science is about questioning, and if our own galactic future was so dynamic, perhaps the universe's ultimate beginning was not as settled as we thought. This realization that even galaxies have finite, dramatic lives opened the door to question everything, including the very first moment of creation. Number 22. The universe has no beginning and no end. The Big Bang Theory posits a singular starting point. The steady-state model proposed in 1948 says the universe has always been here. Fred Hoyle, Thomas Gold, and Hermann Bondi argued that the universe is eternal. They claimed it looks roughly the same at all times and in all places. To account for the observed expansion of the universe, they proposed a radical idea. New matter is continuously created out of nothing. This creation happens slowly and evenly throughout space, just enough to form about one hydrogen atom per cubic meter every few billion years. This would maintain a constant density as the universe expands. The model was elegant. It required no special beginning, no moment of creation. It obeyed what they called the perfect cosmological principle, which states the universe is homogeneous and isotropic in both space and time. For a time, it was a serious competitor to the Big Bang. Fred Hoyle, a brilliant and famously stubborn astronomer, actually coined the term Big Bang on a BBC radio show in 1949. He meant it as an insult, a way to mock the idea of the entire universe springing into existence from a single point. The model's main problem was evidence. In 1965, Arno Penzias and Robert Wilson discovered the cosmic microwave background radiation, or CMB. This faint uniform glow of microwaves bathing the entire sky was a perfect prediction of a hot, dense, early universe cooling over time. The Big Bang model explained it as the leftover heat from creation. The steady-state model had no natural explanation for it. It could not account for a universe that was once hotter. Later observations also showed that the universe has evolved. Quasars and radio galaxies, for example, are found mostly at great distances, meaning they existed in the early universe but are rare today. This directly contradicts the idea that the universe is the same at all times. Despite the evidence, Hoyle and his collaborators never gave up. They later developed a modified version called the quasi-steady-state cosmology, which we will discuss later. But the original steady state, in its simple, elegant form, could not survive the onslaught of observational data that pointed to a universe with a history, a universe that was once very different from what we see today. Number 21. The universe is a projection on a 2D surface. Our universe appears to have 3 dimensions of space, plus 1 of time. The holographic principle suggests this is an illusion. It proposes that all the information contained within a volume of space can be described by a theory that lives on the boundary of that region. It's like a hologram. A 3-dimensional image is encoded on a 2-dimensional surface. This idea emerged from the study of black holes. In the 1970s, Jacob Bekenstein and Stephen Hawking discovered that the entropy of a black hole, a measure of its information content, is proportional to the area of its event horizon, not its volume. This was a shock. It suggested that the information about everything that has ever fallen into a black hole is stored on its 2-dimensional surface. In the 1990s, Gerard Hooft and Leonard Susskind extended this idea to the entire universe. They proposed that our entire 3D universe could be a holographic projection of information stored on a distant 2D surface, possibly at the cosmological horizon, the edge of the observable universe. This challenges the Big Bang by fundamentally redefining what space and time are. In the Standard Model, the Big Bang is an event that happens within space-time. In the holographic model, space-time itself is an emergent property. It's not fundamental. The fundamental reality is the 2D code on the boundary. Some recent studies of the cosmic microwave background have found anomalies and patterns that are slightly better explained by a holographic model than by the standard Big Bang with inflation. For instance, calculations of fluctuations in the CMB are simpler and fit the data slightly better in a 2D holographic framework. The main challenge for this model is that it is incredibly difficult to test. We don't know what the 2D surface is, where it is, or how the projection works. It also raises profound philosophical questions. If our reality is a projection, what is the projector? What is the underlying reality? It's a model born from the most advanced theories of quantum gravity and string theory, and it suggests that the universe is fundamentally a repository of information, and the 3D world we experience is just one way of reading it. Number 20, the universe bounces instead of beginning. The Big Bang Theory leads to a singularity, a point of infinite density and temperature where the laws of physics break down. This is a major theoretical problem. Loop Quantum Cosmology, or LQC, offers a way out. LQC applies the principles of quantum mechanics to gravity itself. In this framework, space-time is not a smooth, continuous fabric. It is made of discrete, indivisible units, or quanta of space. Think of it like a piece of cloth. From a distance, it looks smooth, but up close, you can see the individual threads. According to LQC, you cannot squeeze space down to an infinitely small point. There is a minimum possible size, a fundamental atom of space. This changes everything about the beginning of the universe. As you go back in time, the universe gets denser and denser, but it never reaches a singularity. Instead, when it reaches a certain maximum density, quantum gravity effects create a powerful repulsive force. This force stops the collapse and causes the universe to bounce. In this model, our Big Bang was not a beginning from nothing. It was a big bounce from a previous contracting universe. This contracting universe might have looked very different from our own, or it could have been one in an endless cycle of expansion and contraction. The Big Bounce model solves the singularity problem. It also provides a potential explanation for some of the large-scale features of our universe that the standard Big Bang model struggles with, like the smoothness of the cosmic microwave background. The theory predicts specific signatures that could be found in the CMB or in gravitational waves from the early universe. For now, these signatures have not been definitively detected. LQC is a work in progress, part of the broader effort to unify general relativity and quantum mechanics. But it presents a compelling alternative to a singular beginning, replacing it with a potentially infinite cycle of cosmic death and rebirth. Number 19, the laws of physics evolved with the universe. The standard Big Bang model assumes that the fundamental constants and laws of physics have been the same for all time. But what if they haven't? The theory of cosmological natural selection, proposed by physicist Lee Smolin in 1992, suggests a kind of cosmic evolution. The basic idea is that universes are born from the collapse of matter into black holes. When a black hole forms, a singularity is created at its center. Smolin proposed that at this point, a new universe is born on the other side of the singularity with slightly different physical constants. This is analogous to biological reproduction with random mutation. In this scenario, fecund universes are those whose physical constants are tuned to produce the maximum number of black holes. Why? Because more black holes mean more offspring universes. Our universe is remarkably good at making black holes. The constants of nature, like the strength of gravity and the mass of the neutron, seem finely tuned to allow for the formation of massive stars, which are the precursors to black holes. If these constants were even slightly different, stars either wouldn't form, wouldn't live long enough, or wouldn't collapse into black holes. So, according to this model, we find ourselves in a universe that is good at making black holes, because those are the types of universes that reproduce most successfully. This is a radical departure from the Big Bang. It suggests that our universe is not a one-off event, but part of a vast, multi-generational cosmic ecosystem. It also provides a potential explanation for the fine-tuning problem, the question of why our universe's constants are so perfectly set for the existence of complex structures like galaxies and stars. The major weakness of the model is that it is currently untestable. We have no way of observing other universes or confirming that they are born from black holes. It remains a fascinating but speculative idea, one that applies the principles of Darwinian evolution to the cosmos itself. Number 18, time itself is expanding, not space. Chronometric cosmology, developed by Irving Siegel in the 1970s, offers a different interpretation of cosmic redshift. The standard model says redshift is a Doppler effect caused by galaxies moving away from us as space itself expands. Siegel's model argues that space is not expanding, it is static, as Einstein originally preferred. The redshift instead is an intrinsic property of the relationship between different frames of reference in a curved cosmic spacetime. In this model, time is not universal. The relationship between the energy of a photon and its frequency depends on the curvature of the cosmos. As light travels vast cosmic distances, it loses energy, causing it to shift towards the red end of the spectrum. This is not due to expansion, but to the fundamental geometry of the universe. This model claimed to explain the redshift distance relationship without needing a Big Bang, dark energy, or cosmic inflation. It predicted a quadratic relationship between redshift and distance, rather than the linear one predicted by the Hubble-Lemaitre law at close distances. For a while, Siegel and his supporters argued that astronomical data actually fit their model better than the standard one. However, as more and more data accumulated, especially from distant supernovae and the cosmic microwave background, the evidence overwhelmingly favored the expanding universe model. The standard model could explain the CMB, the abundance of light elements, and the large-scale structure of the universe in a way that chronometric cosmology could not. Siegel's work is now considered a minority view, but it serves as a powerful reminder that even the most fundamental assumptions, like the idea that space itself is expanding, can be challenged. It forces us to ask whether we are interpreting the data correctly or if there is another way to look at the evidence. Number 17, our universe is one bubble in a boiling multiverse. The theory of eternal inflation suggests that the rapid expansion of the early universe, called inflation, did not happen just once. Instead, it is an ongoing process that is constantly spawning new universes. Imagine a pot of boiling water. Our universe is just one bubble that formed and separated from the eternally boiling background. This background space is expanding at a fantastic rate. In some small patches, the inflationary energy field decays, and a bubble universe like ours is formed. Inside this bubble, inflation stops, and a more leisurely expansion, like the one we see today, takes over. The laws of physics and the fundamental constants inside each bubble could be different. This creates a multiverse of countless bubble universes, each with its own unique properties. This model challenges the Big Bang by saying it wasn't a unique, one-time event. Our Big Bang was just one of many, a local event in a much larger, eternally inflating cosmos. This provides a potential solution to the fine-tuning problem. If there are an infinite number of universes with different laws, it's not surprising that we find ourselves in one that has the right conditions for life. It's like asking why we live on Earth instead of Jupiter. We live on Earth because it's the planet that can support us. The other planets still exist. Similarly, other universes might be sterile and empty, but we, by definition, must live in a habitable one. This is known as the Anthropic Principle. The biggest problem with eternal inflation is that, like many multiverse theories, it is nearly impossible to test. The other bubble universes are causally disconnected from ours. We can never reach them or observe them. Some physicists argue that it is therefore not a scientific theory, as it cannot be falsified. However, some researchers are looking for subtle clues, like a potential bruise on our cosmic microwave background that could have been caused by a collision with another bubble universe in the distant past. Number 16, the universe was born from a sea of strings and branes. String theory is one of the leading candidates for a theory of everything. It proposes that the fundamental constituents of reality are not point-like particles, but tiny, vibrating, one-dimensional strings. This theory requires the existence of extra spatial dimensions beyond the three we experience. In the late 1990s, this led to the development of brane cosmology. A brane, short for membrane, is a multi-dimensional object that can move through the higher dimensional space, often called the bulk. In this model, our entire universe is a three-dimensional brane floating in a higher dimensional bulk. One of the most popular brane cosmology models is the ekpyrotic scenario, which means conflagration or fiery in Greek. It proposes that our Big Bang was not a beginning from a singularity, but the result of a collision between two parallel branes in a higher dimension. Imagine two vast flat sheets moving through a 4D space. They slowly drift towards each other over an immense period of time. When they collide, the kinetic energy of the collision is converted into the matter and radiation of a new, hot, dense universe. This universe then expands and cools just like in the standard Big Bang model. This model avoids the singularity problem. It also provides an alternative to cosmic inflation for explaining why the universe is so flat and uniform. The uniformity is a result of the branes being very large and flat before they collided. The ekpyrotic model makes specific predictions about the spectrum of primordial gravitational waves. So far, our measurements are not precise enough to distinguish it from the predictions of inflation. It remains a compelling and mathematically sophisticated alternative, suggesting that our universe's fiery birth was not a singular event in our spacetime, but a cosmic fender bender in a hidden, higher dimensional reality. Number 15, electricity, not gravity, shapes the cosmos. Plasma cosmology and its more recent variant, the electric universe, propose that electromagnetism plays a far more significant role in the universe than is acknowledged by mainstream cosmology. The standard model assumes that on the largest scales, gravity is the only force that matters. Plasma cosmologists argue this is a mistake. They point out that 99.9% of the visible matter in the universe is in a plasma state. Or plasma is an ionized gas, meaning its atoms have been stripped of their electrons. This makes it highly responsive to electric and magnetic fields. This model was pioneered by Hannes Alfvén, a Nobel laureate in physics. He argued that the universe is threaded with vast electric currents called Birkeland currents and powerful magnetic fields. These forces, he claimed, are responsible for the structure we see in the cosmos. For example, they propose that galaxies are not formed by the slow gravitational collapse of gas clouds. Instead, they are formed at the intersection of huge Birkeland currents, which pinch the plasma into a spiral shape. And stars, they argue, are powered not just by internal nuclear fusion, but also by external electrical energy from these galactic currents. Plasma cosmology rejects many of the core tenets of the Big Bang. It does not require a beginning in time. It rejects the existence of dark matter and dark energy, explaining the anomalous rotation of galaxies and the accelerated expansion of the universe through electromagnetic effects. It also denies the existence of black holes, suggesting that the dense objects at the centers of galaxies are plasmoids, which are dense, magnetically confined balls of plasma. Mainstream cosmology largely dismisses these ideas. Critics point out that while electromagnetism is powerful, it tends to cancel itself out over large scales, leaving gravity as the dominant force. They also argue that plasma cosmology cannot explain key observations like the cosmic microwave background, the abundance of light elements like hydrogen and helium, or the precise details of the large-scale structure of the universe. Number 14, the speed of light is not constant. One of the cornerstones of modern physics, central to both relativity and the Big Bang model, is the constancy of the speed of light. But what if it isn't constant? Variable speed of light VSL models propose that the speed of light was much higher in the early universe. This idea was independently proposed in the 1990s by John Moffat and the team of Andreas Albrecht and João Magejo. A much faster speed of light in the early universe could solve some of the major problems that the theory of cosmic inflation was designed to fix. For example, the horizon problem asks why distant regions of the universe, which should never have been in causal contact, have the same temperature. Inflation solves this by saying they were once close together and then were rapidly pushed apart. VSL solves it by saying that light traveled so fast in the early universe that information had time to travel between these distant regions, allowing them to reach a uniform temperature. Similarly, the flatness problem asks why the universe is so geometrically flat. VSL can solve this by allowing influences to propagate much faster, smoothing out any initial curvature. In a VSL universe, the fabric of space-time could change its properties, allowing light to travel at different speeds at different times. This is a profound challenge to the foundations of physics. It would mean that Einstein's theory of general relativity is not the complete picture. The main difficulty for VSL models is creating a consistent theory that changes the speed of light without violating other well-tested physical laws. It's not as simple as just changing the value of in the equations. Doing so affects everything from causality to the conservation of energy. Proponents are working on developing comprehensive theories that can make unique, testable predictions. One potential signature could be a specific pattern in the fluctuations of the cosmic microwave background that differs from the predictions of inflation. While still a fringe idea, VSL shows that even the most sacred cows of physics are open to question in the quest to understand the universe's origins. Number 13, the universe is a self-reproducing fractal. The idea of a fractal universe suggests that the distribution of matter in the cosmos is a fractal at all scales. A fractal is a pattern that repeats itself at different magnifications. Think of a coastline or a snowflake. As you zoom in, you keep seeing the same kinds of complex patterns. In the 1980s and 90s, astronomers like Luciano Pietranero argued that galaxy surveys showed a fractal pattern. The way galaxies cluster into groups into clusters, and clusters into superclusters seem to follow a consistent fractal dimension as far as we could see. This directly challenges a core assumption of the Big Bang model, the cosmological principle. This principle states that on large scales, the universe is homogeneous and isotropic, meaning it looks the same everywhere and in all directions. A fractal universe is, by definition, not homogeneous. It is clumpy and structured at every level. If the universe is a fractal, it could be infinite in extent and age, removing the need for a Big Bang. The observed expansion could be an illusion or a local phenomenon in an eternal structured cosmos. However, as galaxy surveys have become larger and have probed deeper into space, the evidence for a fractal structure has weakened. Most cosmologists now agree that the universe does appear to be clumpy on small scales up to a few 100 million light years, but on scales larger than that, it smooths out and becomes homogeneous, just as the standard model predicts. The most recent surveys, like the Sloan Digital Sky Survey, have mapped millions of galaxies and have found a scale of homogeneity, a distance at which the fractal pattern breaks down. While the idea of a purely fractal universe has largely been ruled out, the study of fractal structures has been very useful in understanding how galaxies and clusters form. It highlights the complex, non-uniform nature of the universe on all but the very largest scales. Number 12, gravity gets weaker as the universe ages. In 1937, the brilliant physicist Paul Dirac noticed a curious coincidence. The ratio of the electrical force to the gravitational force between an electron and a proton is a huge number, roughly 10 raised to the power of 40. The age of the universe expressed in atomic units is also a number of the same magnitude. Dirac speculated that this was not a coincidence. He proposed that these numbers were related and that the strength of gravity, represented by the gravitational constant g, might actually decrease over time. This is the core of the Dirac large numbers hypothesis. If g were stronger in the past, it would have profound implications for cosmology. It would affect the expansion rate of the universe, the formation of galaxies, and the evolution of stars. A stronger gravity in the past would have made stars burn through their fuel much faster. It would also have slowed down the expansion of the early universe more effectively than in the standard model. This idea was later developed into a more complete cosmological model by Karl Branes and Robert Dicke, known as Brans-Dicke theory. In this model, g is not a constant, but is determined by a scalar field that permeates the universe. This field can evolve over time, causing the strength of gravity to change. For a while, this was a serious alternative to general relativity. However, decades of precise measurements have put very tight constraints on any possible variation of job. Experiments ranging from lunar laser ranging, bouncing lasers off mirrors left on the moon by the Apollo astronauts, to observations of binary pulsars have shown that if g is changing at all, it is changing incredibly slowly, far too slowly to have the dramatic effects Dirac envisioned. While Brans-Dicke theory has not been completely ruled out, the standard model with its constant g remains a much better fit to the available data. The hypothesis remains a tantalizing what-if that forces us to test our assumptions about the fundamental constants of nature. Number 11, the universe is not the same in all directions. The standard model is built on the cosmological principle, which assumes the universe is isotropic the same in all directions. But what if it isn't? Anisotropic models explore this possibility. One of the earliest and most famous examples is the Gödel universe, proposed by the logician Kurt Gödel in 1949. He found a solution to Einstein's field equations that described a rotating universe. In this universe, there is a preferred direction of rotation. An object's inertia would be different depending on which way it was moving relative to the cosmic rotation. A bizarre consequence of Gödel's model is that it contains closed time-like curves. This means that it would be possible, in principle, to travel back in time and meet your past self. While Gödel's specific model was ruled out because it didn't include an expanding universe, the general idea of an anisotropic universe has been revisited many times. In recent years, analysis of the cosmic microwave background from the MAP and Planck satellites has revealed some strange anomalies. There are unexpected large-scale patterns and alignments that seem to pick out a preferred direction in space. This has been dubbed the axis of evil because it challenges the fundamental assumption of isotropy. For example, some of the largest scale temperature fluctuations in the CMB seem to be aligned with the plane of our solar system. This could be a coincidence or a sign that we are not correctly accounting for local effects, or more radically, it could be a sign that there is a real intrinsic anisotropy in the universe. If the universe is not the same in all directions, it would force a complete rethink of the Big Bang model. It could mean that our position in the universe is special in some way, or that there are unknown physical laws that operate on cosmological scales. For now, the statistical significance of these anomalies is still being debated, but they represent one of the most significant observational challenges to standard cosmology. Number 10, our universe started cold, not hot. The Standard Model is often called the hot Big Bang theory. It posits an incredibly hot, dense beginning. The cold Big Bang model, proposed by David Laser at Harvard in the 1960s, suggests the opposite. It proposes that the universe began in a state of near absolute zero in a smooth, uniform, and cold configuration. In this model, the energy required to create the matter and heat of the universe came from the gravitational energy of the initial state. As the universe began to expand, gravitational instabilities caused the initially smooth matter to start clumping together. This process of clumping and collapsing released enormous amounts of gravitational potential energy, which was then converted into the heat and radiation we observe today. This gravitational heating is what ignited the stars and created the hot plasma of the early universe. This is a bottom-up model of structure formation where small clumps form first and then merge to create larger structures like galaxies and clusters. This is in contrast to the top-down scenarios that were popular at the time. The cold Big Bang model had some successes. It could explain the formation of structure without requiring the tiny initial density fluctuations that the Standard Model needs. However, it failed to explain several key observations. Most importantly, it could not account for the perfect black body spectrum of the cosmic microwave background. The CMB's spectrum indicates that the entire universe was once in a state of perfect thermal equilibrium, a hot, dense soup. It is very difficult to achieve this level of equilibrium in a universe that started cold and heated up through gravitational collapse. The model also struggled to produce the correct abundances of light elements like helium and deuterium, which are a cornerstone prediction of the hot Big Bang's primordial nucleosynthesis. Number 9, dark matter doesn't exist. Gravity itself is different. The standard cosmological model, lambda CDM, requires two mysterious components to work: dark matter and dark energy. Dark matter is needed to explain why galaxies rotate faster than they should, and why galaxies and clusters move so quickly. Modified Newtonian dynamics, or MOND, proposed by Mordechai Milgrom in 1983, says dark matter is not real. Instead, our understanding of gravity is wrong. MOND suggests that Newton's second law of motion, F equals ma, is only an approximation that works at the high accelerations we experience in our daily lives and in the solar system. At the extremely low accelerations experienced by stars at the edges of galaxies, the law changes. Specifically, MOND proposes that at these low accelerations, the gravitational force is stronger than predicted by Newton or Einstein. This extra pull is what holds galaxies together without the need for dark matter. The remarkable thing about MOND is how well it works. Using only the visible matter in a galaxy, MOND can predict its rotation curve with stunning accuracy, often better than dark matter models, which have more free parameters to tune. It explains a number of observed regularities in galaxies, such as the Tully-Fisher relation, which connects a galaxy's luminosity to its rotation speed. However, MOND has its own problems. The original version was not a complete theory and did not incorporate relativity. While relativistic versions of MOND have been developed, they are often complex and have their own issues. MOND also struggles to explain the behavior of galaxy clusters. While it can reduce the need for dark matter in clusters, it usually cannot eliminate it completely. Most critically, Mond cannot explain the observations of the cosmic microwave background or the large-scale structure of the universe as successfully as the lambda CDM model with dark matter. The bullet cluster, where two galaxy clusters have collided and the dark matter appears to have separated from the normal matter, is often cited as direct evidence for dark matter and a major problem for Mond. Number 8, a static universe can explain redshift. One of the foundational pieces of evidence for the Big Bang is that the light from distant galaxies is redshifted, which is interpreted as the expansion of space. The tired light hypothesis offers a different explanation. First proposed by Fritz Zwicky in 1929, it suggests that the universe is not expanding. Instead, photons of light simply lose energy as they travel over vast cosmic distances. This loss of energy would cause their wavelength to increase, shifting them towards the red end of the spectrum. The farther a galaxy is, the longer its light has traveled, and the more energy it has lost, resulting in a greater redshift. This would explain the Hubble-Lemaître law without requiring an expanding universe or a Big Bang. There are several proposed mechanisms for how light could lose energy. Perhaps it scatters off interstellar dust or gas, or maybe there is some unknown interaction between photons and space-time itself. The problem with all tired light models is that they fail to match key observations. First, if light is scattering, it should also be blurred. Distant galaxies should look much fuzzier than they do. They don't. Second, and more decisively, is the observation of time dilation in distant supernovae. In an expanding universe, not only is the light stretched, but time itself is stretched. This means that a supernova explosion in a distant galaxy should appear to happen in slow motion. We have observed this effect precisely as predicted by the expansion model. A tired light model where the universe is static does not predict this time dilation. The light would get redder, but the duration of the event would be unchanged. This observation, along with the model's inability to explain the cosmic microwave background, has led to tired light hypotheses being rejected by the vast majority of physicists. Number 7, the universe will end in fire and be reborn. The conformal cyclic cosmology (CCC) is a model proposed by the renowned physicist Sir Roger Penrose. It is a cyclical model of the universe, but with a twist. It suggests that the universe goes through an endless sequence of aeons. Each aeon begins with a Big Bang and ends with an infinitely expanding, cold, empty universe. The key to Penrose's idea is the concept of conformal invariance. He argues that in the very distant future, when the universe is empty of all matter and consists only of massless particles like photons, the concept of scale, both in time and distance, becomes meaningless. An infinitely large, cold, empty universe becomes mathematically equivalent to an infinitely small, hot, dense one. At this point, a conformal transformation occurs, and the end of the previous aeon becomes the Big Bang of the next aeon. This cycle can repeat forever, eliminating the need for a single, unique beginning. The model challenges the standard Big Bang by saying our beginning was not the ultimate beginning, but just one transition in an infinite chain. CCC makes a startling and potentially testable prediction. Penrose argues that the supermassive black holes from the previous aeon would have evaporated via Hawking radiation right at the very end of that aeon. The energy from these final pops would have left an imprint on the Big Bang of our own aeon. These imprints should be visible today as specific circular patterns of low temperature variance in the cosmic microwave background. Penrose and his collaborators claim to have found evidence of these Hawking points in the data from the MAP and Planck satellites. However, their statistical analysis is highly controversial. Most other cosmologists who have looked at the data have concluded that these patterns are not statistically significant and are likely just random fluctuation. The search for these echoes of a previous universe continues. Number 6, we live in an eternal cycle of creation. The Quasi-Steady-State Cosmology QSSC was developed in the 1990s by Fred Hoyle, Jeffrey Burbidge, and Jayant Narlikar. It was an attempt to revive the old steady-state model in a way that could account for the new evidence that had discredited it, such as the cosmic microwave background. QCS proposes that the universe is not just expanding smoothly. Instead, it is undergoing a long-term expansion superimposed with shorter-term cycles of expansion and contraction. These are mini-bangs or creation events, not one single big bang. These creation events happen every 20 to 30 billion years, and they are not singularities, but are driven by a hypothetical creation field similar to the one in the original steady-state model. This field has negative energy and is what drives the expansion of the universe. The model suggests that matter is not created smoothly throughout space, but in localized bursts of creation near the centers of massive galaxies. These creation events would be extremely energetic, which the model uses to explain phenomena like active galactic nuclei and quasars. In this view, the cosmic microwave background is not the leftover heat from a single Big Bang. Instead, it is the thermalized starlight from previous cycles of the universe. The model proposes that interstellar space is filled with tiny iron and carbon needles that are very efficient at absorbing starlight and re-radiating it as microwaves. QSC attempts to explain the observed abundances of light elements by suggesting they are cooked up in stars during the various cycles, not in a single primordial fireball. The model has struggled to gain acceptance. Most cosmologists argue that its explanation for the CMB is contrived and cannot reproduce the observed perfect black body spectrum. It also has difficulty matching the detailed observations of large-scale structure and the precise measurements of the expansion history of the universe from supernovae. Number 5, mass is not constant, it grows over time. What if the mass of all particles in the universe is increasing? This is the core idea of the growing mass, or scaling model, proposed by Christoph Wetterich. It is another attempt to explain cosmic redshift without an expanding universe. In this model, the universe is static, or only slowly expanding. The observed redshift of distant galaxies is caused by the fact that the atoms in those galaxies were less massive in the past. Here's how it works. When an atom emits a photon of light, the energy of that photon, and thus its color, is determined by the mass of the electrons in the atom. If an electron in a distant galaxy had less mass when it emitted a photon billions of years ago, it would have emitted a lower energy, redder photon. By the time that photon reaches us today, our electrons are more massive. When we compare the incoming photon to the light emitted by our modern, more massive atoms, it appears redshifted. In this model, the entire universe, including all our measuring rods and clocks, is evolving together. The mass of everything is increasing. This means that the universe isn't getting bigger, everything in it is just getting heavier. This is a very difficult idea to test, because if everything is changing scale together, it's hard to find a fixed reference point. However, the model does make some predictions that could differ from the standard model, particularly concerning the very early universe and the process of nucleosynthesis. The standard model's successful prediction of the abundances of helium, deuterium, and lithium depends critically on the laws of physics and the masses of particles being constant during the first few minutes after the Big Bang. Or a model where particle masses are rapidly changing would likely predict very different abundances. So far, the standard model's predictions remain a much better fit to the observed data. Number 4, the universe is a sea of matter and antimatter. The standard Big Bang model has a baryon asymmetry problem. For some reason, the early universe produced slightly more matter than antimatter. For every billion antiquarks, there were 1,000,000,001 quarks. The matter and antimatter annihilated each other, leaving behind the small surplus of matter that makes up everything we see today. But why was there a surplus? The endoplasma model developed by Hannes Alfvén and Oscar Klein proposes that there wasn't one. It suggests the universe is perfectly symmetric, containing equal amounts of matter and antimatter. They are just separated into different regions. This model, rooted in plasma cosmology, suggests that in the early universe, a plasma of matter and antimatter, the ambiplasma, separated into distinct domains like oil and water. We just happen to live in a very large domain of matter. Other domains, perhaps as large as galaxy clusters, would be made of antimatter. When a matter domain and an antimatter domain meet, they would annihilate each other at the boundary. This annihilation, the model proposes, would be a powerful source of energy and could explain high-energy cosmic phenomena like gamma-ray bursts. This model avoids the need for a mysterious asymmetry at the beginning of the universe. The primary challenge is observation. If there were large regions of antimatter in the universe, we would expect to see a significant gamma-ray background radiation from the annihilation happening at the boundaries between matter and antimatter regions. We do not observe such a background. The observed gamma-ray background is very low and can be explained by other known astrophysical sources. Furthermore, we have not seen any evidence of anti-galaxies or anti-stars. When cosmic rays, which are particles traveling through space, hit our atmosphere, we detect almost exclusively matter particles, protons, helium nuclei, and no antiprotons or anti-helium nuclei that would be expected if they were coming from antimatter galaxies. Number 3. The Big Bang was a white hole explosion. A black hole is a region of space-time where gravity is so strong that nothing, not even light, can escape. A white hole is the mathematical opposite. It is a region of space-time from which nothing can enter, and from which matter and light are explosively expelled. White holes are valid solutions to the equations of Einstein's general relativity, but they have long been considered a mathematical curiosity with no physical reality. The white hole cosmology model proposes that the Big Bang was, in fact, a white hole. This idea connects the Big Bang to the physics of black holes. One version of this model, proposed by Lee Smolin and others as part of loop quantum gravity, is called Planck star cosmology. It suggests that when a massive star collapses, it doesn't form an infinitely dense singularity as predicted by classical physics. Instead, quantum pressure halts the collapse when the core reaches a fantastically dense but finite state called a Planck star. This object eventually rebounds in a quantum bounce. For an outside observer, due to extreme time dilation, this process would take billions or trillions of years. During this time, the object would appear as a stable black hole, but eventually the bounce happens and the object explodes as a white hole. The model suggests that our Big Bang could have been the white hole explosion resulting from a Planck star that formed in a different, older universe. This creates a link between black holes and the creation of new universes, similar to the cosmological natural selection model. This idea is highly speculative, but offers a potential physical mechanism for the Big Bang, rooting it in the known physics of stellar collapse rather than an unknowable initial singularity. It might even be testable. Some physicists have suggested that if the Big Bang was a white hole, there might be specific observable signatures left behind in the cosmic microwave background or in the spectrum of primordial gravitational waves. Number 2. The universe is made of discrete space-time atoms. Both of the pillars of modern physics, general relativity and quantum mechanics, have a problem with infinity. General relativity predicts infinite density in a black hole singularity, and quantum field theory is plagued with infinite values that have to be removed through a process called renormalization. In causal set theory, CST attempts to solve these problems by proposing that space-time is not continuous. It is discrete, made of fundamental, indivisible atoms of space-time. These atoms are not arranged in a regular grid, they are sprinkled randomly, and their density determines the curvature of space-time, which we perceive as gravity. The fundamental relationship in this theory is not distance or time, but causality. The space-time atoms are linked by a concept of before and after. This creates a partial ordering, a network of cause and effect relationships that builds up the fabric of spacetime. In CST, the Big Bang singularity cannot exist. You cannot have an infinite number of spacetime atoms in a finite volume. The universe must have had a first atom, a first event, from which all others followed. The expansion of the universe is simply the continuous addition of new spacetime atoms to the cosmic set. Causal set theory is a radical approach to quantum gravity. It predicts a tiny inherent jitter in the propagation of light, which is currently far too small to be measured. More significantly, it provides a potential explanation for dark energy. The theory predicts that the random fluctuations in the number of spacetime atoms would lead to a small but persistent cosmological constant, causing the expansion of the universe to accelerate. The value predicted by the theory is remarkably close to the observed value of dark energy, which is one of the biggest mysteries in standard cosmology. CSCST is still in its infancy and faces many technical challenges, but it offers a unique bottom-up approach to building the cosmos from the simplest possible ingredients, discrete events, and the arrow of causality. Number one, the universe is a computation. The digital physics, or it from bit hypothesis, is perhaps the most fundamental challenge to our understanding of reality. It proposes that the universe itself is, at its core, a form of computation. The idea, famously summarized by physicist John Archibald Wheeler with the phrase "it from bit," suggests that every particle, every field, every physical object derives its existence from information. In this view, the laws of physics are not fundamental descriptions of a pre-existing reality. They are algorithms. The state of the universe is the output of a massive computational process. The Big Bang was not an explosion of matter and energy, but the moment the cosmic computer was switched on and the program started running. This model suggests that properties we think of as continuous, like space, time, and energy, might actually be discrete, like the pixels on a screen or the clock cycles of a processor. If the universe is a simulation, it could provide answers to some of the deepest mysteries in physics. The fine-tuning of the physical constants might not be a coincidence, but could be programmed parameters. Quantum weirdness, like entanglement and superposition, might be a natural consequence of how the simulation's code is optimized. This is not just a philosophical idea. Physicists like Seth Lloyd have calculated the potential computational capacity of the universe. Others are searching for experimental evidence. If we live in a simulation running on a discrete grid, there might be subtle effects. For example, the highest energy cosmic rays might not travel at the same speed in all directions, as their movement would be constrained by the orientation of the underlying cosmic grid. So far, no such evidence has been found. The idea of a computational universe blurs the line between physics, information theory, and philosophy. It challenges the very notion of what it means for something to be real. It suggests that the ultimate reality is not matter or energy, but information, and that the cosmos we inhabit is the unfolding of a grand cosmic calculation.